In today's note, we are going to be reviewing all of the simple probability concepts that we've looked at so far. So we're going to look at some basic theoretical and experimental questions. We're going to look at some mutually exclusive and non-mutually exclusive questions, and we're going to look at independent versus dependent questions. So the idea is, again, just to review some of these, and hopefully we are confident with recognizing the different types of events, as well as the correct formulas to use when dealing with those events. So this video is going to be a little bit different. I will read through the questions with you. We'll go over and we'll highlight some key information, things that you want to look at, and then what we'll do is I'll pause the video or recommend that you pause the video so that you can try this on your own, and then we'll come back with the full solutions. So before we get into that, I just want to look at a summary of all of the concepts that we've looked at so far in this unit. So looking at them, we've looked at theoretical, or what's sometimes called classical probability. So this is what should happen. And basically the number of outcomes is known and each outcome is equally likely. So for example, rolling a die. Each outcome is equally likely, and we know what all the outcomes are. They're 1 to 6. Same with, say, pulling or drawing a card. We know there are 52 outcomes and each outcome is equally likely. The formula for that, the probability of A or event A is equal to the number of times A, or the number of A outcomes over the total number of set outcomes, or the total number of outcomes available. Experimental or empirical probability, this is what did happen. So this is where the number of outcomes is determined through experimentation. So this is where you are running trials, you're actually doing something, and you are basing the probability off of that. The formula looks very similar to the last one for theoretical, except instead of NS on the bottom, we have NT, which just means the number of trials. Range of probabilities. So we've talked about this briefly, but this is basically stating that the probability of an event is between 0 and 1 inclusive. So it can be anything between 0 and 1. 0 being the lowest, or basically saying there's no chance that it's happening, and 1 being the highest, or 100%, basically saying it is absolutely certain that this will happen. Complementary events. Again, we've talked about this. The complement of event E is the set of all outcomes in a sample space that is not included in E. And we usually denote it or mark it by E with an apostrophe or the dash. So basically it's saying that if you have event E, say it is rolling a 6, then the complement to rolling a 6 is all of the outcomes that are not that. So that is every roll that would not be a 6. So 1, 2, 3, 4, and 5. And basically the idea is that the probability of an event plus the probability of its complement has to equal 1, which is again the total amount of probability that you can have, the greatest amount that you could have. The addition rule, this is what we used for mutually and non-mutually exclusive events. So it's used for when finding the probability of at least one of two events occurring, and usually this is indicated by or. So again, usually we see or in the question. Not always, but again, it's one or the other. Again, mutually exclusive for the formula, we are adding the two probabilities together, and this is where they're mutually exclusive. There is no overlap. They do not happen at the same time. Non-mutually exclusive, this is where we add the probabilities of the two events together, and then we subtract when they both occur at the same time. Or in other words, we're subtracting the overlap, right? Because when they're mutually or non-mutually exclusive, that means that there is a case of an overlap. So for an example, an event like that would be a heart and a face card. You can draw a card that is both a heart and a face card. So if you were to add up the two probabilities of hearts, or drawing a heart and drawing a face card, you would overlap, or you would double count some outcomes. So that's why you have to subtract that overlap. The multiplication rule, so this is used to find the probability of two events occurring in sequence, so one after another. And usually we see this indicated by and. We may have also seen it as followed by, but basically one event follows another, or basically both events are happening one after another. Independent means that they are not affected by the previous one. So they're two independent events. They do not affect each other. And in this case, we multiply our probabilities of those two events together. If they're dependent, meaning that one event relies or is affected by the outcome of the previous event, we still multiply them together. However, that second probability is called a conditional probability because it's the probability of event B on the condition that event A occurred. So that means that in some cases, the probability for the second event is going to be changing because of what we've done in the first event. So you do have to be careful because you may have to calculate, you may have to change your calculation or think about changing your calculation for that second probability. Because again, it would have changed from the first one. So you do have to be a little bit more careful with independent and dependent events. So that's again the summary of the simple probabilities. So let's look at some example questions. So in the first one, a restaurant offers 2 appetizers, salad or nachos, and then 3 entrees, fish, chicken, or beef. Draw a tree diagram to show all the possible combinations of appetizers and entrees. And then the 2 questions that we're going to use or answer based off of that tree diagram is what is the probability of a vegetarian dish or choosing a vegetarian dish, so meaning no chicken or no beef, and what are the odds in favor of having chicken. So if we go through, we'll go through and underline kind of the key things. So 2 appetizers is key. We're told what they are. And we have 3 entrees as well, which is key, and we're told what they are. We have our 2 questions. What is the probability of a vegetarian dish? And that's basically saying no chicken or beef. What are the odds in favor of having chicken? So those are kind of the key things there. So again, I'm going to recommend that you pause the video and try to do this one on your own. And we'll come back with what our full solutions are. So looking at this question, we have our tree diagram. I've kind of broken it up into 2 parts for our 2 appetizers, but we can see the different combinations. Salad with the 3 entrees, and then nachos with the 3 entrees. So what is the probability of a vegetarian dish, meaning no chicken or beef? In this case, that means the only options that are acceptable are the ones with fish. So if we look at our outcomes, we could see that there are 2 outcomes out of 6 possible outcomes. So in this case, 2 over 6, which equals 1 over 3, which equals 33%. What are the odds in favor of having chicken? So in order to figure this out, we would need to figure out what is the probability of having chicken and what is the complement to that, so not having chicken. So again, looking at the combinations that have chicken, there are 2 out of 6, or 1 over 3. And the probability of not having chicken would just be the opposite of that, or that probability subtracted from 1, which would be 4 out of 6, or 2 over 3. We set those 2 probabilities together, or as a ratio together, because it is in favor of having chicken. We want the probability of having chicken first. So 1 over 3 to 2 over 3, which we can create an equivalent ratio of 1 to 2. Moving on to the next question. A blue die and a red die are rolled. What is the probability of each event occurring? A blue 3 and a red 4. B, not a blue 4 and a red 6. So again, a couple key things we want to figure out. First, 2 dies are being rolled. Just keep it color coded. A blue die and a red die. We're looking for a blue 3 and a red 3. And then we'll underline this because this will be key, not a blue 4, and a red 6. So again, those keywords should tell us what type of probability or event we're dealing with, and from there, hopefully we can determine what type or what formula we should be using. So again, I recommend you pause the video to try this on your own. So looking at these two questions, we should have recognized that with the "and," those are referring to either independent or dependent events. In this case, when we're rolling two different dice together, or two dice in any case, they are independent events. What I roll on one die does not affect or change the outcome or the probability of what I roll on the second die. So regardless though, I should be multiplying my two probabilities together. For a blue 3 and a red 4, well, if I'm using a standard die, the only time a 3 can come up is 1 out of 6, and for a 4, it's 1 out of 6 as well. The color red doesn't really matter, or the color blue doesn't really matter, it's just indicating that I have two different dies. So 1 out of 6 times 1 out of 6 equals 1 out of 36, which works its way down to 2.8%. For B, the probability of not a blue 4 and a red 6. So again, still two independent events. For not a blue 4, that means every other outcome except for 4 on that blue die. In this case, that means there are 5 out of 6 possibilities, so 5 over 6, because basically those are the numbers 1, 2, 3, 5, and 6, multiplied by the probability of a red 6, which is 1 out of 6, so I get 5 over 6 times 1 over 6, which is 5 over 36, which works out to about 13.9%. In the next example, Seth rolls a pair of 6-sided dice 4 times and gets doubles, which means the same number of dots showing on each die twice. What is the experimental probability of rolling a double? What is the theoretical probability of rolling a double? And C, explain why the answers to part A and B differ. So again, I recommend you pause the video and try this one on your own. So coming back and looking at this, again, I didn't really underline anything, so hopefully you were able to recognize that we needed to underline at least the fact that he's rolling a pair of 6-sided die 4 times and gets doubles twice. Keeping in mind then experimental probability and theoretical probability are going to be using two different sets of numbers or sets of outcomes. So for A, the experimental probability, we're using the numbers given to us in the question. So in this case, I've written out the full formula just so that we can see the difference. We're looking for the number of times doubles occurred over the total number of trials. In this case, it's 2 over 4, which works out to 1 over 2, or 50%. For B, theoretical probability, this is where you would use something like the chart that we talked about in one of the previous lessons that shows all of the outcomes when rolling a die, or rolling two dice. So the number of times doubles can occur is 6 times, 1 for every number. So double 1s, double 2s, double 3s, 4s, 5s, 6s. Out of the total set of outcomes, in this case there are 36 different outcomes, so 6 out of 36, which reduces to 1 over 6 and is roughly 16.7%. So for C then, explain why these answers differ. Again, remember, experimental probability is what did happen based on an experiment or what happened in the past, and theoretical probability is what should happen. The theoretical or the experimental probability should get close to theoretical if we do more trials. So if we do more trials, say increase it to rolling the die 20 times, 30 times, 100 times, we should get closer to that 16.7% chance of getting doubles. And again, that goes back to the law of large numbers that we talked about in a previous lesson. So Next example, John's pencil case contains 3 red pens, 4 purple pens, and 6 black pens. What is the probability that John will draw a red or a black pen? So again, here there's a couple things we want to underline. 3 red pens, 4 purple pens, 6 black pens. And in our question, what is the probability that John will draw a red or a black pen? So you can highlight what we're looking for. I would underline or at least recognize that keyword or, because again, that should help us determine what we're looking at. So again, pause the video and try this one on your own. So with this question, by recognizing that it says or, that should indicate that we are looking at mutually exclusive or non-mutually exclusive events. The two events aren't following each other, and in this case, when we're looking at either mutually or non-mutually exclusive, these ones would be mutually exclusive. The two events do not happen or can't happen at the same time. If you're pulling a single pen, it will not be both red and purple. So in this case, we are looking at mutually exclusive events, which means we should not be subtracting anything. We should just be adding the two probabilities together. So in this case, we're adding the probability of drawing a red and the probability of drawing a black pen. We should get 9/13 for the 3 red and 6 black pens, 13 pens in total. And this works out to about 69.2%. So there's a 69.2% chance or probability that John will draw a red or a black pen. In this question, several studies have been conducted on the effectiveness and safety of the H1N1 influenza vaccine. One study found that in a group that received the actual medication, the drug was 87% effective. In a group that received the placebo, there was a 10% effective rate. If the study used 400 people to receive the placebo and 600 people to get the actual drug, determine the probability that any person in the study will A, receive the drug and not get sick, and B, not get sick. So there's a lot to unpack here because this is a more wordy question and you will find these. So let's go through and underline some of the key things. So one study found that in a group that received the actual medication, so this is key, so it received the actual medication, it was 87% effective. In a group that received the placebo, it was a 10% effective rate. If the study used 400 people to receive the placebo, let's kind of keep the same colors because we're talking about the same thing. So 400 people received the placebo and 600 people got the actual drug. In our questions, some of the key words we can underline is just and. So receive the drug and not get sick. So again, those are some key things that we should be looking at to help us solve this question or these questions. Again, pause the video, try this one on your own, and we'll come back with the full solutions. So coming back to this example, this one may have been a little bit tricky because there were some things we had to calculate that weren't, so there were some probabilities that were given to us and there's some probabilities that we had to calculate on our own. So for A, we're looking at to receive the drug and not get sick. But because we're looking for the probability of any person in the study, so that means there are two events that have to happen. One, they have to receive the drug and not get sick. So these are looking at dependent versus independent events. And again, because of that and, we need to take that into consideration. So that tells us what we should be doing with our probabilities. We should be multiplying them. Now, in terms of conditional probability for dependent events, because these two events are linked, right? You receive the drug, that will affect the probability of you, or of it being effective or you not being sick. So there is a conditional probability. However, in this case, it is given to you. So you are told what the probability of you being healthy is if you're given the drug. Right? And again, we underlined those in the previous one. So the only thing we had to calculate in this case what was the probability of selecting a person who received the drug. So the probability of receiving the drug and not getting sick, so I indicated that with the complement of being sick. So the probability of receiving the drug, there were 600 people out of a total of 1,000, and I'm going to multiply that by the effectiveness of the drug, 87%, 0.87, because that means that there's an 87% chance that you are not getting sick. So 600 over 1,000 times 0.87 works out to about 0.522 or 52.2%. So there's a 52.2% chance, or the probability of picking a person who received the drug and did not get sick was 52.2%. For B, not getting sick, this one we had to think again a little bit further. You may have already taken the last example or the last answer and said, well, we've already determined what the probability of someone not getting sick was. We found it. However, there was a second situation. And that second situation was you could take the placebo and also not get sick. Right? Because there was a certain effective rate for those that received the placebo. So in this case, we're looking at two different situations. The probability of receiving the drug and not getting sick, and the probability of receiving the placebo and not getting sick. Those two together would make up the probability of not getting sick. Because when we're looking at not getting sick, it could be either the people that received the drug or the people that received the placebo. So this is kind of an independent and dependent event question tied in with a mutually exclusive and a non-mutually exclusive event tied in. So we already figured out the probability of receiving the drug and not getting sick, and we take the same idea for the placebo. What's the probability of selecting someone who received the placebo? Well, it's 400 over 1,000 multiplied by the probability of not getting sick. Let me just put that complement mark there, which was 10%, and you got basically 4%. So there's a 4% chance that you would pick someone who took the placebo and did not get sick. So to find the probability of selecting someone who did not get sick in general, you would add those two different situations together, because it doesn't matter if they took the drug or if they took the placebo. The main thing we're looking at is, did they not get sick? And when we add those two together, we should work out to about 56.2%. The next example, the table below has data about the fate of the passengers in the sinking of the Titanic ocean liner in 1912. A, what is the probability that if a person was from the first class or second class, the person survived? So again, a couple things to add here. And we're looking at people from the first class or the second class, and the key thing we're looking at is, did they survive? So again, I recommend pausing the video so you can try this one on your own. So in this question, this one may have been a little bit tricky to think about, because it does say or, however, there's not really two events that we're looking at. So in this case, they're just saying the group of people that we're going to be looking at solely is only in the first and second class. So if we look only at those numbers, what is the probability that a person survived? So this is actually just a kind of like almost an experimental probability question. How many people survived? Well, I've highlighted them: 55, 113, 6, 13, 78, 25, out of how many people in total were there in first and second class. And we can add all those up. And again, we should get 290 over 561, which works out to about 51.7%. So again, even though it included or, you have to think about what is it asking. Who are we looking at here? Right, so this one was a little bit tricky in the way that it was worded, considering what we had talked about so far. Moving on to the next one, there's two questions here. What is the probability that if a person was from the third class, they survived? So this one is very similar to what we just talked about, and this one's almost a little bit easier to understand compared to the last one. So we're only focusing on the third class group. And then C, what is the probability a person survived if the person was in first class and not a man? So again, we go through person survived in first class and not a man. So again, I recommend you pause the video to try this on your own. So again, in this one, for B, we're looking only at people in the third class and whether they survived or not. So when we add up all our numbers, we should find that in the third class, 172 people survived out of 699, which works out to about 24.6%. For C, what is the probability a person survived if the person was in first class and not a man? So in this case, it may seem like it's a independent and dependent event. However, there's not two events here. Again, we're only looking at a specific group of people. So we're looking at the first class and not men. So if I look at the first class and not men, I've highlighted in green, I can see that 113 women and 6 children survived out of a total of 124 women and children, which works out to about 96%. So again, we do have to be careful, and again, I'm kind of getting caught up on this as well. We do have to be careful about what words we look at, and we have to really think about, are there two events going on here, or is this just indicating what event or what overall event we are looking at? In the last two examples, we are looking at for the probability of survival if you're in second class and not a man, and in third class and not a man. So hopefully from the last example, we should recognize now, and it makes it a little bit easier on what we're actually trying to solve, or how we're trying to solve. So again, I recommend you pause the video to try this on your own. So coming back to these two questions, again, looking at the same kind of criteria as we did in the past, or the last example, we're looking at only the people in the second class who are not men, and what is their probability of survival. So looking at the numbers of people in second class who are not men, we find that there are 78 women and 25 children that survived out of, adding it all up, it works out to about 116 women and children in total. So there are 103 survivors out of 116 women and children, which works out to about 88. Change that. It works out to about 88.8%. And for the third part, looking again just at the third class and not men, so again only women and children, so the probability of being in third class and not a man and surviving, we have basically 113 survivors or women and children that survived out of a total of 258 women and children in the third class overall, which works out to about 43.6%. So again, this was a good one to leave off on because it does make us think about, again, we do look for and or to indicate mutually exclusive, non-mutually exclusive, independent, and dependent. However, we have to be careful and make sure we're looking at two specific events, or is it just describing the group of people that we're looking at? So again, we do want to be careful with that. But again, overall, we should by now hopefully recognize what those different events are, how to recognize them, and what to do when we recognize them. And again, if you are having struggles with some of these concepts, again, please go back and look at the previous lessons.